Well, folks, I made another computer. I spent about a year on this build, and I think the time spent thinking things out and designing it out, the patience with having to scrap current ideas and come up with new ones, I think finally paid off for me. You're looking at a video of the system in operation. The old system is here in the background that I created, I believe, in 2020 during the pandemic. This current year, we didn't, of course, have the pandemic, but I still had some sufficient time of my own that I could sit down, on cold days during winter and think things out and think about things that I liked about the old system and wanted to continue, and things that just weren't necessary anymore. And so this is the second pass, and it's turned out quite well, and I hope you'll agree. About a year ago, I bought a Prusa 3D printer, and I'm glad that I did because it allows me to design physical objects outside of just printed circuit boards. I bought it mainly, I have to admit, to build some items that would be used in this build here, and you're seeing some of that already. This is the front display panel that you saw in the beginning of the video, only I have it on its side so you can see that it's actually comprised of two PCBs, and they are interconnected by these long connectors down here. It receives all of its information from two sources. This 50-pin connector that goes to the CPU board gets the majority of the signals about what the system is doing, and then here in the background you can see a 6-pin ribbon that's coming from the UART so that I can display what the UART is up to. This first board here contains the majority, actually for the most part, all of the logic needed to drive the display. This second board here is mainly just to mount the visual components, such as the 7-segment drivers, the LEDs that provide a visual indication of what it's doing. I created these little spacers on a 3D printer so that I could at least have, for the most part, everything at a uniform height from the board. It made mounting this faceplate a lot easier. I printed these as well, these little spacers that the screws go into that do a nice job of keeping everything at a uniform distance from one another. So another 3D build that works out. What you can see here also is my version of a card cage. It's also 3D printed, and it mounts to the backplane that we'll cover next. Here's the backplane with the card cage on both sides. Again, 3D printed. Little slots for the cards go right through here. The backplane allows for up to 9 connections or 9 cards. I don't use them all, of course, at this point, but they're there in case I do. The power supply is here in the background. Its leads connect to this main input, and then there's additional terminal blocks here. For instance, these two are used to feed the floppy disk drives. One of the things that I did on this system that I learned the hard way from the previous system, I made the power traces much wider to carry much more current. The prior system had very inadequate widths, and I saw some substantial drops in voltage from the power supply to a board in particular, and I traced that back to just not having the best design when it came to power. So another lesson learned. The card cage guides here simply mount to the bottom of the PCB with a bunch of bolts coming up from the top, and there's actually some additional holes here that allow me to mount this backplane on an underlying support, so that if I want to, I can attach this to a piece of wood just to make things more stable. So that's the backplane. Here's a picture of the CPU card. Here's the 1802 running at 4 megahertz. I threw a little nano processor on here. The previous system had it too, and no, it doesn't. It doesn't really supply any major functionality to the overall system. It does, however, allow me to control this system remotely. And an example of that, I have a program on my home computer that interfaces to this Nano. I can basically start and stop the CPU from reset run modes. And while the system is reset, I can use the Nano to upload a program, such as the operating system that I'm constantly fiddling with, or another program such as the editor that I'm writing. That way I don't have to worry about burning EPROMs repeatedly just to get things right. I can, of course, reach over to the computer itself, this one, and push run and reset all I want, but I find it much more productive to run a session on my home computer where I'm basically calling the shots from an interface that I wrote. So up here is the 50-pin connector that, through the ribbon cable connects to the front panel. And this is the CPU board. Here's the UART board. I'm using what I call the standard 1854 at the heart of things. And I have a single clock source that is of an appropriate rate, that through a flip-flop I can either have a 115K baud rate or a 57K, and that's jumper selectable. The old system, I could program the baud rate from a program itself, or I should say I could set the baud rate. I didn't use it that often. I found that I enjoyed the 115K speed all the time, so I thought there's no point in re-engineering something that I don't use, so I got rid of it. About the only cheating that I do aside from that Nano is I use one of these little FTDI friends that allows me to hook this UART board to the USB on my computer, and it does a fine job of interfacing without too much of a footprint, I might add. Here's the 6-pin header where the ribbon cable goes to that connects the UART status display to the front panel. And again, this is the UART board. Here's the memory board. And it currently has 256K of memory on it. These chips down here are basically chip select logic. The rest of this stuff is static RAM. This chip right here I can replace with an EEPROM, a 32K EEPROM, once my OS gets stable enough that I can burn it to an EEPROM and enjoy it to be there all the time. This other stuff here, these three are 32K RAMs. This here is a 128K RAM chip. And I put some test points here while I was testing out the system. Now you might ask yourself, how in the heck can Jeff access 256K of RAM from a 16-bit address bus? Well, I'll get to that here next, but here's the memory card. Here's what I spent the majority of time on over the winter. It's what I call my Memory Manager Unit, or MMU. I'm most proud of this device here. I spent quite a bit of time writing out design after design after design, emulating activity in my own mind, because of course nothing like it existed at the time. And I'm pleased to say the first generation of this board worked upon day one. I was quite happy when I saw it in operation. The 1802 is a 16-bit computer. It addresses up to 16 bits of memory, or 64K. So it's to say that anything greater than that would occupy address lines 16 and 17. That's what this board manages for me. That's all it does. It's quite busy because the 1802 has 16 registers. And aside from DMA, which actually, now that I think about it, even DMA utilizes register 0. But in order to access memory from the 1802, one of those 16 registers has to be involved. Any register can be your program counter, or your data pointer, basically. You have the flexibility of setting that. This board is constantly keeping track of what the CPU is doing. It understands what instruction was fetched. Basically, once that instruction's fetched, there's information that's been burned on this EEPROM that determines what happens during the execute state. Or in the event of a DMA cycle, it knows that register 0 is going to be involved. Or during an interrupt, it knows to bank in a certain bank of memory for the interrupt. It's basically I/O driven, just like any other card. It has its group selection right through here, and right now I have it set to respond to group 60, decimal 60. Okay, and there's 3 instructions that this system, or that this board, I should say, understands. I can make it active. I can not make it. I can basically deactivate it, and I can tell it for each register what page or bank of memory that it needs to switch to when that register is being used. The register memory is actually down here, and I have to say this chip here is extreme overkill, but I needed something to be fast, so I think this is, if I'm not mistaken, I think this is a 70 nanosecond response time for a chip. There's certain timing requirements that I had to meet in terms of so many, clock cycles after the TPV pulse. I had to, trap something. I had to essentially capture what the current state was going to be next. And so I had to use these 4538 timers, and I put adjustable trimmer caps on here, so that I could fine-tune the time when these pulses would get fired. There's one here, and there's one down here. So, it's quite a bit of components here, but it does the job, and it does it well. Again, through a program, I can say, hey, when register 11 is accessing memory, I want you to use bank 01. When register 12 is using memory, I want it to bank or address, say, bank 2, completely independent of one another. And this thing will switch the banks essentially by toggling those 2 additional address lines during the execute phases. And it knows it intercepts the setting of a program counter, and it intercepts the setting of the X register. So, for instance, when you're doing an STXD to store something off to say, via the X register, in the execute phase, it could be completely different bank than what the fetch one was. So it's quite pleasing to see it run. Again, I have to basically be honest. I gave this about a 50-50 shot as to working. I mean, everything in my mind, all the simulations I was doing in my head and so forth, gave me a good degree of confidence that this thing was going to work. But I was kind of holding out for some disappointment. And, I mean, to my surprise, it was working on day one. I basically hooked it up to my scope, logic analyzer, and everything appeared to be going according to plan. So it works. This is the MMU. Last but not least is the floppy disk board. I actually made this board after the other components were put into use and tested, mainly because I thought, if the system design stunk, I didn't want to really perpetuate a bad design. This board here uses a different chip. The first system used, I think it was a 765, UPD 765, if I'm not mistaken, or 764. I get confused. This one used a 37C65. It is a little bit more advanced in the fact that it has its own data separator logic, so all that other support logic that was on the old system goes out the window. And the only real stuff other than this chip here is the circuitry needed to interface with my system, the I/O commands and so forth and so on. And for the most part, I kept a lot of that from the old system here. This system here has 2 headers. Only one is in use for 2 floppy drives. If I get the crazy idea to run 4 3.5-inch floppy drives, I have that option to expand. But until then, I'm going to keep this area up here free and clear, but it is out there. You'll notice a preponderance of test pins that I put on this board, mainly because I didn't know how this guy was going to operate compared to the other IC. So I wanted the ability to monitor what this thing was doing. Again, I didn't have any nasty surprises with it. It turns out to be working quite well. It is powered by a 16 megahertz chip here, or clock chip, half can, I think they call these, supplying the primary timing signal into this chip, and then this thing here, I guess, is capable of generating all the internal frequencies that it needs to do whatever it does. So I'm quite happy with this board as well. I have to give a mention to Design Spark Mechanical. It's a bit of software that was for free for a while, but like a lot of great things, they decided to fall into a subscription model. So you got to pay, so much per month to be able to use it. The great thing is I started using this while it was still free, so it didn't really cost me anything to learn how to use it. And honestly, I think anyone building retro computers that wants to custom make parts like I did, if you can afford to get a 3D printer, it's well worth it here. This is the faceplate that I've drafted on here that covers the front of the board. Some of the other things that I made, let's see here. Here's the card edge. Now, there's only one half of it, and the reason being is that the other piece of software that you're not going to see here is the slicer. Prusa has their own slicer that comes with their printer. I can basically mirror this, so I only need to make one half of it, and I let the slicer software create the mirror image of it. So I spent some time on this bad boy, but it was well worth it because it came out really well. I mentioned the backplane has the ability to be mounted on an anchor, if you will, and that's what this is. This is what sits underneath that. And I'll admit it takes a while to get used to all the dimensioning, because with this 3D printer, you might need a 3.5 millimeter diameter hole for a screw. I can tell you that it might need to be 3.7 millimeters, simply because the 3D printers, they don't have a perfect tolerance in terms of the bead of PLA material that they place down. It can get smashed. There's all sorts of variances that you have to take into consideration. And I found that it helps to make a small model of something, like, say, just one of these screw holes here, and just to see if the screw will fit in there nicely. And after that, after you get to learn your printer, and what it's capable of and what it isn't. Let's see, the faceplate. I mentioned on the face, underneath the faceplate, I have those little headers for the LEDs. I was looking into actually getting some headers for some LEDs, and I thought, well, heck, I can just print those as well. So I created these bad boys here and printed them out, and it works out too. So get yourself a 3D printer if you can afford it. They're well worth it, and I personally recommend the Prusa. I didn't want to go the Creality route because, number one, so many different models of that thing, and two, when I would go onto the forums when I was doing my research, it seemed to be almost a hobby in itself, in the sense that drove me away. I did not want something that I had to fight constantly to use. I wanted a 3D printer specifically as an appliance, and Prusa seemed to fit that desire better, than the Creality. and I'm pleased with it. It hasn't let me down. I've had it for over a year now. I haven't had any jams, clogs, or malfunctions. They're constantly updating their firmware, and I'm quite pleased with it. No, Prusa or Design Spark Mechanical is not paying me for this endorsement. I just know from my own use, I highly recommend it. So get yourself a 3D printer. I can't stop mentioning that. It's well worth it. So, to wrap things up, you're looking at my editor here. I use Notepad++ to write my assembly code. I don't get to program today as much as I'd like to. Everything is so graphical, you know, and a lot of people, you know, that's what they grew up with. But you know, I grew up on the mainframe world, and so everything had to be coded line by line. And there were times I dabbled in assembler even on the mainframe. And I think that's one of the reasons why I keep doing this, is because I enjoy coding. I think it's an excellent exercise for the human mind, and writing this assembly language gives me a little bit of pleasure in creating something that's useful. Just to show you a little tidbit here, here's how the OS starts up. You know, I mentioned that the page or bank assignments by register is stored in a static RAM. I couldn't count on that RAM to be initialized as 0 upon power up, so that was what gave me the idea of disabling the MMU so that the 16 and 17 address lines would be ground or logic level low upon startup. And that's what I'm doing here after I select it. And then I set every single register 0 through 15 to start out in bank 0, unknown state. I clear some working storage. That's my COBOL days talking. Clear out the working storage, and then I enable the MMU. I basically say, you are now in control, pal. And then the rest of the operating system takes off after that. So the manipulation of the MMU, I wrote some routines that basically allow me to call a routine that I call set page. And I pass it a single byte, where the high nibble is the register and the low nibble is the page, and it goes off and does its thing. It's very short, actually, here. And there's something else that I wanted to show here now that I think about it. I apologize for the small delay, but let's see here. Oh, yes. When it comes to branching, MMU doesn't get along with branching. To be honest with you, I didn't design it to. The majority of the operations occur through the call and routine, or the call and the return methods. Okay, and for that we have the standard call and return technique that RCA came up with here. And if I stop talking for a second, I might be able to locate the package that has that information. Okay. Let's see if I can go really quickly to a call here. Okay, so here's a call where I'm calling this procedure. Didn't have to change much. The only thing you might notice is that there's a byte here. This is the page that we go off to based on the address, or I shouldn't say based on the address. This is the 16-bit address here that's resolved. This is the page that follows. The standard call and return was simply changed so that instead of pushing a high and low to the stack, it also passes a page. Okay, and I used some memory in page 0 to keep track of what each register was set to, so I don't have to bother with the MMU. And like the second part of the call routine, we're basically taking the address that was in register 3 and moving it off to the old link, or I should say to the new link register. This is what the new return value will be. It still does the same thing, only what I need to do here is I take the value that page 3 has, and I increase the pointer here, and I slam it down into 6. And then I go off and I say, hey, Mr. MMU, for page 6, here's your new here for register 6, here's your new page. And it works quite well. System is slightly slower than the previous one, only because it's got a little bit more to do. But at 4 megahertz, it's still clocking pretty well. I have got a lot of tweaking to do in the OS. That was difficult. The OS that I had written previously was on the old system, and it didn't have any MMU. So I had to go through all of the OS and basically adjust all the logic to handle the fact that it may be getting called from a program in another page. And that's one of the projects that I'm working on now is writing an editor, again, just for the heck of it. I'm not going to be writing any dissertations or major documents on it. I might use it to do some programming, you never know. But again, it's just for the fun of it. And so this editor, I thought, gee, the OS routines will be in bank 0. The editor program itself will be in bank 1. And then the storage that the editor uses, mainly the document or the text file or the assembly file that you're editing, that still has 2 additional pages of storage that I can read and write from. So I've got high expectations for this editor once I get done with it. Again, that's once I get done with it, because I do have a family. I still have a very stressful and demanding job, so I get to play with it when I have the time. So, but that's it for the system. I hope you enjoyed what you watched, and if you have any questions, feel free to leave me a comment. I think I put my email address on my page information. Just know that my first name is Jeff, my last name is Truck. I have an account with Gmail, and there's a period between my 2 names. So if that doesn't tell you enough to send me an email, I can't really be any more obvious than that. I don't want somebody, or I should say some robot, to lift my email address off any more than it has. I'm still getting a ton of spam. Good Lord, when are they going to fix that? I don't think ever, but it is what it is. So thanks for spending some time with me on this project. I'm real happy with what I've got here. If others would like to know what I've done, I'll be more than happy to tell you. Till then, talk to you later. Bye-bye.